Have you ever wondered why certain metals are just incredibly strong, or how engineers actually design those super advanced alloys for aerospace? Well, the secret is all about how materials behave when they're heated up and cooled down. Today, we're unpacking the ultimate blueprints of material science, phase diagrams. We'll see how the fundamental properties of the stuff all around us are secretly dictated by their thermal histories.
So here's the crucial takeaway. Heating and cooling a material fundamentally changes its internal microstructure. And a phase diagram, it's basically the map that helps us navigate those exact changes. It tells us exactly what state a material is going to be in under specific conditions, like temperature, pressure, and composition. Now, even though these diagrams represent stable, equilibrium states, they're the absolute baseline we use to figure out how to manipulate materials to do exactly what we need them to do. Here's how we're going to break it down today. First, the map of materials. Second, phases and solubility limits. Third, mapping a single component. Fourth, binary systems, mixing metals. And finally, number 5, the lever rule explained. All right, let's jump straight into section 1, the map of materials, defining the states of matter. To read a phase diagram, we really need to nail down what exactly a phase is. Think about a massive iceberg out in the ocean. Right there, you have 3 totally familiar phases of water coexisting. You've got the solid ice of the iceberg itself, the liquid water making up the ocean, and the vaporous clouds floating up in the sky. Now, while they aren't perfectly in equilibrium in nature, they're the perfect starting point to understand this. So let's get a formal definition. A phase is a homogeneous portion of a system that has uniform physical and chemical characteristics. Basically, it has clear boundaries. For example, ice and liquid water are chemically identical, right? They're both H2O, but they are physically distinct. One's solid, one's liquid. That makes them 2 completely separate phases. If you mix 2 things and they form a single, uniform substance with no clear boundaries, you've got 1 phase. But if there are boundaries with abrupt changes in properties, boom, multiple phases. Moving right along to section 2, phases and solubility limits, the sweet science of saturation. Now, things get really interesting when we start mixing phases together. Think about stirring sugar into your morning coffee or tea. As you add sugar, it dissolves into a single liquid phase, basically a syrup. But there's a limit, right? If you keep dumping sugar in, eventually it just sits at the bottom of the mug. You've officially hit the solubility limit. At that exact moment, your single liquid phase transforms into a 2-phase system. You have the saturated liquid syrup and the solid, undissolved sugar crystals. And crucially, that solubility limit depends entirely on the temperature. By following a few simple steps on a phase diagram, we can predict exactly when a solution becomes saturated. Say we locate 20 degrees Celsius for our temperature and find the corresponding boundary. At that temperature, the limit is exactly 65% sugar by weight. So, if your mixture is, say, 60% sugar at 20 degrees, you've got a pure liquid syrup. But if you push it to 70%, you've crossed the boundary, and now you have a mix of syrup and solid sugar. Section 3, mapping a single component, pressure and temperature. When we map out pure H2O, the phase boundaries clearly show us exactly where 2 phases coexist in equilibrium. If you shift the temperature or the pressure enough to cross one of those boundaries, a phase transformation happens, like melting or boiling. But the really wild part is the invariant triple point, where all 3 boundaries meet. For water, at a very specific, tiny fraction of an atmosphere of pressure, solid ice, liquid water, and water vapor can literally exist simultaneously in perfect equilibrium. If you tweak the temperature or pressure even a tiny bit from that exact spot, at least 1 phase just completely disappears. Fun fact, by the way, scientists actually use this exact triple point of water to calibrate high-precision thermometers.
All right, section 4, binary systems, mixing metals, from water to high-tech alloys.
Now that we've got the hang of single components, let's level up to binary systems, because this is where things get really exciting. With a pure unary system like water, the main variables are just temperature and pressure. But in a binary system, like the industrial metal alloys used in modern manufacturing, we're usually processing things at a constant atmospheric pressure. So instead of pressure, our second variable is the composition of the mixture itself. We're mapping out temperature against the weight percentage of the 2 different metals. Before we map anything, we need to understand a massive concept, isomorphous. The copper-nickel system is a classic isomorphous system. This means these 2 metals dissolve into each other perfectly at any concentration, and not just when they're melted liquids, but as solids too. They can pull this off because copper and nickel happen to share the exact same face-centered cubic crystal structure, they have almost identical atomic radii, and similar electronegativities.
Basically, they're the perfect metallic match. Imagine a map for copper-nickel where temperature goes up the side and the weight percent of nickel runs along the bottom from 0 to 100. Up top, above the Liquidus line, everything is a glowing molten liquid. Down below, under the solidus line, everything is a solid alpha phase. Now picture a molten mixture of exactly 35% nickel slowly cooling down. As the temperature drops and crosses that top liquid phase boundary at around 1260 degrees Celsius, solid alpha phase crystals start forming right there in the melt. We have officially entered the two-phase region. So, this brings us to a really critical question. We know we've got a mix of solid crystals and molten liquid hanging out in this middle transition zone. But how on earth do we determine the specific chemical makeup of those newly formed solid crystals versus the liquid that's left over? I mean, they aren't both just going to stay exactly 35% nickel.
The solution to this is actually brilliant. We use something called a tie line, or an isotherm. In that two-phase region, you establish a perfectly horizontal line at your current temperature, say 1250 degrees Celsius. This line stretches from the liquid boundary on one side to the solid boundary on the other. To find the exact compositions, you just drop straight down from where your tie line hits those boundaries. The drop from the liquid side might tell us our remaining liquid is currently 31.5% nickel. And the drop from the solid side, it shows our newly formed solid crystals are actually 42.5% nickel. The overall mix is still 35%, but the nickel is actively redistributing itself as it cools.
Which brings us to Section 5, the lever rule explained, calculating phase amounts. All right, we've mapped the borders, we know exactly what phases are present, and we've found their chemical compositions using the tie line. But there's one final piece to this engineering puzzle. Sure, we know the liquid is 31.5% nickel and the solid is 42.5% nickel, but what are the actual mass fractions? At 1250 degrees Celsius, is our alloy mostly liquid or is it mostly solid? To figure this out, we have to use a mathematical concept called the lever rule. The lever rule works literally just like a physical seesaw on a playground. Your overall alloy composition acts as the fulcrum right in the middle. Here's the trick. To find the mass fraction of a specific phase, you don't look at the side closest to it, you actually look at the opposite side. So, to compute the fraction of the liquid phase, you take the length of the tie line segment on the solid side of your overall composition, and you divide it by the total length of the entire tie line. And it works exactly the same way in reverse. To find the mass fraction of the solid alpha phase, you measure the tie line segment extending toward the liquid boundary and divide that by the total length of the tie line. Because we're dealing with a closed system here, the mass of the components perfectly balances out. The sum of your liquid fraction and your solid fraction is always going to equal exactly 1, or 100%. So, let's actually run the numbers for our 35% nickel alloy sitting at 1250 degrees Celsius. Using the lever rule, the math gives us a wonderfully precise answer. At this exact moment in the cooling process, our alloy is exactly 68% liquid and 32% solid. Think about that. Imagine if you could know the exact mathematical ratio of chunks to broth in a bowl of soup. That's basically what we just did for molten metal. The math itself is literally just basic subtraction. To get the liquid fraction, we take the solid phase composition of 42.5 and subtract our overall composition of 35. That's the top of our fraction. Then we divide it by the total tie line length, which is 42.5 minus the liquid composition of 31.5. So 7.5 divided by 11 gives us roughly 0.68. By simply subtracting the weight percentages, a highly complex physical transformation of molten metal becomes a clean, simple equation.
Now you might be wondering, why does all of this meticulous mapping and calculating actually matter? Well, it's because while these phase diagrams show us perfect, slow-cooling equilibrium, in the real world, engineers rarely want perfect equilibrium. If you've ever seen a blacksmith plunge a glowing red sword into a barrel of water, they are intentionally interrupting that cooling process to freeze the metal in what's called a metastable state. It's a non-equilibrium microstructure that persists indefinitely, and it often drastically increases the hardness and the strength of the metal. And that leaves us with a truly fascinating thought. These diagrams, they aren't just academic charts in a textbook, they're literal control panels for reality. Once you know how to read these maps, locating the phases, drawing the tie lines, calculating the fractions, you realize that precisely controlling a material's journey through a phase diagram is exactly how we engineer stronger, lighter, and more advanced materials. A material's thermal history dictates its future. So the next time you step onto a commercial jet or drive over a massive steel suspension bridge, ask yourself, what invisible phase diagrams were manipulated to keep you safe today?